In today's tape, we're going to continue our study of linear combinations. Yesterday, we were interested in linear combinations as related to span and spanning sets. Today, we're going to look at linear combinations in reference to independent-dependent. In future tapes, we're going to put the two concepts together to define other ideas. A set of vectors is linearly independent if and only if no vector in the set can be written as a linear combination of the others. So a set of vectors is linearly independent if and only if no vector in the set can be written as a linear combination of the others. If one vector can be written as a linear combination of the others, the set is linearly dependent. So if I can write one vector as a linear combination of the others, the set is linearly dependent. The set consisting of the vectors 1, 3, 1, 0, 1, 2, 1, 0, negative 5 is linearly dependent. The reason is the vector 1, 3, 1 can be written as a linear combination of the vector 0, 1, 2 and 1, 0, negative 5. To see that, I write 1, 3, 1 is equal to C1 times 0, 1, 2 plus C2 times 1, 0, negative 5. So I'm looking for constants C1 and C2 such that the vector 1, 3, 1 is equal to C1 times the first vector plus C2 times the second vector. And that should be a subscript. So I have 1, 3, 1 is equal to, if I multiply through it, C1 times 0 is 0, C1 times 1 is C1, C1 times 2 is 2C1, C2 times 1 is C2, C2 times 0 is 0, C2 times negative 5 is negative 5C2. Add 0 plus C2 is C2, C1 plus 0 is C1, and I have 2C2 minus 5C2. Equating coefficients, I get C2 is 1, C1 is 3, 2C1 minus 5C2 is 1, which is true for C1 equal 3 and C2 is equal to 1. Because if you can check this one, this will be true. 2 times 3 is 6. 6 minus 5 is 1. So C1 equal 3 and C2 equal 1 makes the equation true. So therefore, vectors 2 and 3 were linear combinations of, was a linear combination of vector 1. Now, in order to prove that they were linearly independent, I would have to prove that none of these could be written as a linear combination of any of the others. That would take a while. It's much easier to work with the concept as follows. A set of vectors S equal to V1, V2 up to Vk in a vector space V is linearly independent if the vector equation C1V1 plus C2V2 plus up to and including CKVK is equal to 0 has only the trivial solution. Now, of course, the trivial solution would be that Ci is equal to 0 for all i's. In other words, C1 would be 0, C2 0, on up to CK 0. If there exists a non-trivial solution, then S is linearly dependent. Now, the advantage of looking at it from this standpoint is that I only have to consider one equation. So I form the linear combination of all the vectors in the set and set it equal to 0. I solve the equation if I get only the trivial solution, then we know that it's linearly independent. If we find a non-trivial solution, a non-zero solution, then it's linearly dependent. I've written the steps out for you. The test for independence, dependence. The first thing you write, or first thing you do, is to write the vector equation C1x1 plus C1v1 plus C2v2 plus out to including CKVK is equal to 0. So that's your first step. Write the vector equation. The second thing you do is write the related homogeneous system of equations. So I can always go from the vector equation into related system of equations. You solve the system for the C's, or solve the system of equations for C1, C2, and so forth. If the system has only the trivial solution, that's 0, 0, all zeros, then the set is independent. If the system has non-trivial solutions, then the set is dependent. Look at an example. Determine whether the set containing the following matrices is linearly independent. So I want to determine whether the set containing the following matrices is linearly independent. Well, the first thing I want to do is to form my vector equation. So I can say C1 times 1, negative 1, 4, 5, plus C2 times 4, 3, negative 2, 3, plus C3 times 1, negative 8, 22, 23 is equal to 0. That's going to give me C1, negative C1, 4C1, 5C1, plus 4C2, 3C2, negative 2C2, 3C2, plus C3, negative 8C3, 22C3, 23C3 equals to 0. C1 plus 4C2 plus C3, a negative C1 plus 3C2 minus 8C3. I'm just adding the components, adding the first components, then adding the second components. I'm going to add the components in row 2, column 1. So it'd be 4C1 minus 2C2 plus 22C3. Then add the components in row 2, column 2. 5C1 plus 3C2 plus 23C3. And of course I can write the 0 matrix as 0, 0, 0, 0. So I have the system C1 plus 4C2 plus C3 is equal to 0. I'm just equating components. I have a negative C1 plus 3C2 minus 8C3 is equal to 0. I have 4C1 minus 2C2 plus 22C3 is equal to 0. I have 5C1 plus 3C2 plus 23C3 is equal to 0. I can write the equation in metric, or the system in metric form as 1, 4, 1, 0, negative 1, 3, negative 8, 0, 4, negative 2, 22, 0, 5, 3, 23, 0. And of course I can solve the system of equations now by row reducing a matrix and read the value of my C's. Well, I used derive to do that. I went in and I authored the matrix 1, 4, 1, 0, 1, 3, negative 8, 0, 4, negative 2, 22, 0, 5, 3, 23, 0. And then I told derive to row reduce. Now to do this, I went to author, expression, row, underline, reduce, and I put in parentheses number 1 and told it to give me this. So I said row reduce the matrix, and then I hit simplify. So once I hit simplify, I can now read that C1 is 0, C2 is 0, C3. Well, there is only the trivial solution. So if I have only the trivial solution, therefore the vectors are independent. In this case, the vectors were 2 by 2 matrices, so I could say the set of 2 by 2 matrices are, or the set is independent. The matrices are independent. Determine whether the set containing the polynomials 2 minus x, 2x minus x squared, 3 minus 2x plus 2x squared is linearly independent. Well, the first step is to write the vector equation. I can write 2 minus x and multiply that by C1. So C1 times the first vector plus C2 times the second vector, which is 2x minus x squared, plus C3 times the third vector, which is 3 minus 2x plus 2x squared, is equal to 0. So C1 V1 plus C2 V2 plus C3 V3 is equal to 0. I get 2 C1 minus C1x plus 2 C2x minus C2x squared plus 3 C3 minus 2 C3x plus 2c3 x squared is equal to 0, which I can write as 0 plus 0x plus 0x squared. I can rewrite this as 2c1 plus 3c3 using those terms, plus a negative c1x plus 2c2x minus 2c3x using the x terms, plus a negative c2 x squared plus 2c3 x squared using the x squared terms, and that's equal to 0 plus 0x plus 0x squared, where I get 2c1 plus 3c3 plus the opposite of c1 plus 2c2 minus 2c3 x plus the opposite of c2 plus 2c3 x squared is equal to 0 plus 0x plus 0x squared. Equating coefficients, I get 2c1 plus 3c3 is equal to 0. A negative c1 plus 2c2 minus 2c3 is equal to 0. A negative c2 plus 2c3 is equal to 0. I can put it in matrix form as 2, 0, 3, 0, a negative 1, 2, negative 2, 0, 0, negative 1, 2, 0. Derive, and I'll author the matrix. You can check to see it's the same one. 2, 0, 3, 0, negative 1, 2, negative 2, 0, 0, negative 1, 2, 0. And I go, once I alter the matrix, I row reduce number 2. I made a mistake on expression 1, so I just removed it. And simplify to get what you see, of course, here, the identity matrix. What that's telling me is that C1 is 0, C2 is 0, and C3 is 0. Again, only the trivial solution. So we have only the trivial solution. Therefore, linearly independent. Now, if derive had given a non-zero solution, such as C1 is equal to 1 or something like that, then we would have said linearly dependent.